Welcome to Math Advice. In this video, let me discuss about Fourier series. That's what is Fourier series, what is the use of Fourier series or applications of Fourier series, and definition of Fourier series. That is what we are going to discuss as a first part in this video. Now, let me start with the introduction of Fourier series. Fourier series is invented by a French mathematician Fourier. He introduced this series in 1822 while he was investigating the problem of heat conduction. He was also a physicist and historian too. The series of sines and cosines is known after him. Next, we have a short look over what are the applications of or uses of this series. So, this is a series of sines and cosine terms, and this series arises in the important practical task of representing the general periodic functions. That is, in short, these are particularly suitable for expansions of periodic functions. It is suitable for the expansion of periodic functions. That is, it is used in, Fourier series is used in signal processing. It is the best application of Fourier analysis because advanced noise cancellation and cell phone network technology uses Fourier series where digital filtering is used to minimize noise and bandwidth demands respectively. And also it is broadly used in telecommunication system for modulation and demodulation of voice signals, also the input and output, and calculation of pulse and their sine and cosine graph. Besides that, it is used in, that is a Fourier analysis or Fourier series is used in image processing, heat distribution mapping, wave simplification, light simplification, random measurement, etc. etc. So, as a whole, I have to say the Fourier series is particularly suitable for expansion of periodic function. Wherever there is a periodic function, that is the phenomenon of periodic function we have used, we can make use of this series and get the solutions. Now, with this short introduction, let me now move on to periodic motion. As I told you already, this Fourier series is suitable only for periodic functions. So, before we move on to what is periodic function in detail with the definition, so let me have a short introduction about what is the meaning of periodic motion. So, based on the name itself, you understand periodic. So, after that, which means the motion is repeated in equal interval of time. Any particular motion, if it is repeated in equal interval of time, then we say that is a periodic motion. So, there are so many types of motions are available. That's linear, curvilinear, rectilinear, etc. So, among those, we have to take only periodic motion. So, periodic motion is a motion that is repeated in equal interval of time. That is a period of time to complete one full cycle. That's period of time to complete one full cycle is nothing but a period. For example, we can say the motion of hands of a clock. Am I right? We can say the motion of a hands of a clock. It will take so up to 12 hours. So it will, for one rotation, so it has to complete it 12 hours. So period of the motion of clock is 12 hours. So next, the motion of earth around the sun. So the motion of the earth around the sun is nothing but in an orbit. This is also in periodic. So once in 365 days or 366 days it completes its one rotation. Again, it's starting to rotate around the sun in the same orbit. Isn't it? It is also periodic. So besides that, I have to say periodic motion is performed, for example, rocking a chair, a bouncing ball, a swing in motion, then already told, as I told you earlier, the earth in its orbit around the sun, and the water wave. These are some of the examples of a periodic motion. So in each of the above example that I have mentioned, the interval time for repetition of the motion is called period. That is, the interval of time for a repetition of motion is called period. So that is after a particular time. For example, let me take the hands of clock. So after 12 hours, it started rotating the same way. So 12 hours, then 22 or 4 hours means it comes to the same point, and so it repeats. That is, after a particular interval of time. So the same thing has to happen again and again, means that the smallest period is a period. That smallest number is a period. That is what we are going to see in the next. What is the meaning of period or primitive period or fundamental period? So as a whole, you should know what is period. So when the same motion repeats itself after equal interval of time, we call it periodic motion. And the period is the time to complete one full cycle. Okay. So with this short introduction about what is periodic motion and period, let me now move on to periodic function. This is what we need now. So a function, as I told you already, periodic means when the same motion repeats itself after equal interval of time, we call it as a periodic motion. Am I right? So a function returning to same value at regular interval. Okay, a function returning to the same value at regular interval means that's a periodic function. And in math term, I have to say this as a periodic function is a function that repeats its value in regular periods or regular interval of time. Okay. So in a regular interval of time, the same thing has at a regular interval of time, the same thing, that is after 2 hours, after 5 hours, after 6 hours, something like that, means the same thing has to happen again and again after a particular period of time. Okay. So if it is so, that type of function we name it as a periodic function. So one of the most examples under periodic function is nothing but a trigonometric function. Trigonometric. This is a very well-known examples under trigonometric functions. The trigonometric functions like sine, cosine, tan, cot, secant, cosecant. Okay, so these are all well-known examples under periodic functions. Because periodic functions are used throughout science to describe oscillations, waves, and other phenomena that exhibits periodically. Whenever we have to move on to periodic phenomena, means definitely we should take of any of the periodic function and express them in terms of series and evaluate it. Okay. So now let's move on to this short introduction. Let me now move on to a definition of what is a periodic function. So a function f of x is said to be periodic if and only if f of x plus p is equal to f of x. This is true for some value of p and every value of x, which means that is after a successive period of time, that is after a particular period of time, the same thing has to happen again and again. So as a simple example I have to take, suppose if you take f of x, nothing but rotation of earth, that is a motion of earth. Okay, motion of earth, if you take f of x as motion of earth, so it will take 366 days or 365 days. Okay, so here p is nothing but 365. So after 365, here if it starts from at this point, if the earth starts its rotation at this point to circle around a sun, so after 365 days it comes to the same point. So again it starts rotating. So around the sun in the same orbit. Okay. So here 365 is nothing but a period. Okay. So this for your understanding purpose I will give 365. Suppose if you take the motion of hands of clock, if you take the motion of hands of clock, it will take 12 hours. So after 12 hours the same thing has to happen again and again. That is at 24 hours again it reaches 12 o'clock. At 48 hours again it reaches 12 o'clock. Am I right? But here 12, 24, 28, here the smallest value is 12. Okay, the smallest value, that is what we call as a period. Okay, that is the smallest value of p for which this equation is true for every value of x is called period or primitive period, sorry, P-R-I-M-I-T-I-V, primitive period or fundamental period. Fundamental period. So whatever that may be the name we have used, so either it may be of period or primitive period or fundamental period of the function f of x. So the smallest value of p. So here we take. So as I told you, periodic function means the same thing has to happen again and again after a particular interval of time. Here we have to take the smallest value. Okay. So that value is nothing but the period or primitive period or fundamental period of the given function f of x. So as in terms of, instead of giving like this practical examples, that's for your understanding. Suppose if I am going to give a function that is an example of a periodic function in a math term, so I have to give an example as a sine curve as an example. This is one of the best example. I am going to give you the sine function, that is a periodic function with period. This is a periodic function with period 2 pi. Because as I told you already, periodic function, that is one of the most important examples of the trigonometric function, because which repeat over the interval of 2 pi radians, that is of 360 degree. Okay, so the sine function is periodic at period 2 pi, because f of, that is instead of f you have sine of x plus 2 pi is equal to sine x. This is true for all values of x. That is, this function repeats on the interval of length. Length of the interval here is 2 pi. Okay, so I am just draw a sine curve here. So this is a sine curve. Okay, sine x. So if it is plus 1 and here you have minus 1, as you know already, it starts at 0 because sine 0 value is 0. So at here this is pi by 2, pi and 3 pi by 2 and 2 pi. Likewise to the negative sides too, that is here minus pi by 2 and minus pi, minus 3 pi by 2 and minus 2 pi. So let's first draw it on the positive side. So at 0 sine curve takes the value pi by 2 means it reaches the value at 1, and again at pi it comes to 0, and 3 pi by 2 means it touches the value minus 1, that is at this point, and 2 pi means it comes to, that is it reaches the point 0. Again for the negative sides too you have the same one, but here at minus pi by 2 means it reaches point minus pi by 2, and pi means touches the point 0, plus 1 and 0. This is the curve, sine curve look like this. So how many times it repeats is no, don't worry. So but the length of the interval here is only 2 pi, 0 to 2 pi. The curve looks like this. Okay. So what is the shape of the curve from 0 to 2 pi? If you extend this up to 4 pi, 6 pi, okay, etc., the shape of the curve seems to be like this. It goes like this. Okay. Okay, it goes like this. So this is a well-known examples of a periodic function. Now, with this short introduction, let me now move on to Dirichlet condition. Because before we move on to the definition of what is Fourier series, let me have a short look over the Dirichlet condition. This is one of the important conditions for the existence of Fourier series. Okay, so any function f of x can be developed as a Fourier series. Generally, a Fourier series can be represented like this. That is, f of x is equal to a0 by 2 plus sigma n is equal to 1 to infinity a n cos n x plus sigma n equal to 1 to infinity b n sin n x. This series consists of only cosine and sine terms. I explain why. Because as I told you already, periodic function. As I told you already, I think you remember that. Periodic function, that's the most important examples are the trigonometric functions, because which repeat over the interval of 2 pi radians, as I told you already under the example of periodic function. But trigonometric function doesn't have only sine and cosine function. It has a tan function, cosecant function, cot, secant, etc. But we have only cosine and sine alone in a Fourier series expansion. Why this happened? That usually the answer for this. So why this happen? If you ask a question like why this happen means you get the answer under this Dirichlet condition. Now, so any function f of x can can be developed as a Fourier series like this means here a0, an and bn, here a0 are called constants. So it satisfies the following three conditions. The first one is f of x is periodic. As I told you already, Fourier series is consists of only only periodic functions. Okay, so Fourier series means it has only periodic functions. So next is single value. So for a given, so it doesn't take it of multiple value function, single, that is for a given input you get only one input, something like this. Okay, so you get one single value and finite. You have to take the value of the function in terms of finite number of terms. So first condition most probably it satisfied. So periodic function, as I told you already, periodic Fourier series is only suitable for periodic functions, and also it should be single valued and also finite. Okay, now let's move on to the second condition. It's one of the very important condition. So based on this alone, we have only these two terms as a Fourier expansion. So f of x has a finite number of finite discontinuities in any one period and no infinite discontinuity. Why? So what is the reason behind this is f of x has a finite number of finite discontinuities. It has a finite number of finite discontinuities and in any one period and doesn't have any infinite discontinuity. So how I am going to explain this is as I just show you a table. This was the table you have learned in your school days, but you have to remember this because while we are evaluating this particular series in terms of Fourier series to particular series, you should know the value of the function at 0, 30 degree, 45 degree, something like this. So theta means sin theta, cos theta and tan theta, and 0 degree means at sin 0 you have 0, 1, 0, am I right? And for 30 degree you have 1 by 2 root 3 by 2 and 1 by root 3, and 45 degree means 1 by root 2, 1 by root 2, 1, and at 60 degree you have root 3 by 2, 1 by 2 and root 3, and at 90 degree you have 0 here 1 and tan 90 infinity, and for 180 degree sin 180 is 0, cosine is minus 1, 0, and at 270 degree here you have minus 1, 0, infinity, and 360 degree means that's nothing but again 0 degree. So the length of the rotation and the internal is 2 pi. Okay, so here look at the values of sine and cosine in all angles, that is 0, 35, 45, 60, 90, 180 and 270 doesn't have any infinite discount, doesn't have any infinity, am I right? But whereas look at the value of theta at 90 and 270 degree, it has the value infinity. That is the meaning of this one. So if you take secant is nothing but 1 by cos, am I right? 1 by cosine is anything by 0 infinity. Suppose if you take cosine 270, secant value at 270 is infinity. So you can't take secant also. Like cosecant. Cosecant is 1 by sine. Sine value at 0 itself 0. So 1 by 0 is anything by 0 infinity. So cosecant value at 0 is infinity. Likewise cot. Cot theta is nothing but 1 by tan. So tan theta is nothing but at 0 itself you get 0. So except sine and cosine, so all the trigonometry having one of the infinite discontinuities, that means infinity. So in your terms, in your simple terms, I have to say infinity in its any of the angle values, that is 90 degree or something like this. That's why I have to take only sine and cosine in Fourier series expansion. So suppose in a 2 mark question, you may expect a question, why we can't express we can't take a cosecant or secant or tan or cot in a Fourier expansion. Why means because it has an infinite discontinuity. Your answer is it has an infinite discontinuity. That's why we can't take these terms in a Fourier expansion. Okay. So the last one is f of x has at the most a finite number of maxima and minima. So if any function satisfies these three conditions, then we can express it in terms of a Fourier series. Okay. Now let's move on to a definition of Fourier series. So very important thing. Now let f of x be a periodic function and satisfies Dirichlet condition. Then f of x can be expressed as an infinite series of this form. that is f of x is equal to a naught by 2 plus sigma n is equal to 1 to infinity a n cos n x plus sigma n is equal to 1 to infinity b n sin n x. Here this is called a Fourier series. Here these constants are called Fourier constants. So using Euler's formula we can find the values of a naught, a n and b n. Okay. Now, so before we move on to the Euler's formula, so as a Fourier series means definitely it should be periodic and it satisfies the Dirichlet condition. That's why we start with the definition of periodic function and have a look over about Dirichlet condition. Then we now in the definition, now we are going to discuss the definition of what is Fourier series and all about it. Okay. Now we make use of the Euler's formula for the Fourier coefficients, like that is to calculate the values of a naught, a n and b n. So if function f of x is defined, I have to take the general interval c to c plus 2 pi. c2, that is x takes the value from c to c plus 2 pi. So if a function f of x is defined in c to c plus 2 pi, it can be expanded as an infinite trigonometric series like this. F of x is equal to a naught by 2 plus sigma n is equal to 1 to infinity a n cos n x plus sigma n is equal to 1 to infinity b n sin n x. Here a naught, which is calculated by make use of the formula 1 by pi integral c to c plus, that is you have to take the least value in the lower limit of the integral c to c plus 2 pi f of x dx, and a n is equal to 1 by pi integral c to c plus 2 pi f of x cos n x dx, and b n is equal to 1 by pi integral c to c plus 2 pi f of x sin n x dx. So this is what the general formula to calculate the Fourier coefficients a naught, a n and b n. So in most of the applications, the interval over which f of x is to be expanded is either minus pi to pi or 0 to 2 pi. So in most of the applications, the interval over which f of x is to be expanded is either minus pi to pi or 0 to 2 pi. So that you have to take c here, so that c in the Euler formula is usually either, minus pi or 0. It is usually either minus pi or 0. Suppose if you substitute c is equal to minus pi, what happened to, there is no change in the inside value of the integral. Okay. So a naught is equal to, if you substitute a naught, c is equal to minus pi, what happened? So a naught is equal to 1 by pi integral c becomes minus pi, means minus pi to minus pi plus 2 pi means you get only plus pi f of x dx. Likewise a n is equal to, there is no change, only the value of the, that is in limit of the integral only alone changes from minus pi to plus pi. b n also minus pi to plus pi. So suppose if c is equal to 0, what happens? If c is equal to 0 means you have the length of the interval 0 to 2 pi. So a naught is equal to, that is a naught is equal to interval from 0 to 2 pi. So nothing is changing. A naught is equal to 1 by pi. Instead of c to c plus 2 pi, you have to take 0 to 2 pi f of x dx. Likewise a n is equal to 1 by pi. Instead of c to c plus 2 pi, you have to take 0 to 2 pi. Like that b n is equal to 1 by pi. Instead of c to c plus 2 pi, you have to take 0 to 2 pi. Only the limit value of the integral alone change, nothing will be changed. Okay, so in most of the applications, the interval over which f of x is to be expanded is either minus pi to pi or 0 to 2 pi. So that's why we have to take these two cases and we have to discuss the problem under these two cases in the next video. Okay, now let me explain. So is a Fourier series that is in pi form. Okay, there are two types of categories we are going to discuss. One is in pi form, another one is L form. So that is under change of intervals we have to discuss L form. First we have to concentrate about pi form. Pi form is nothing but either the interval length is of 0 to 2 pi or minus pi to pi. So these two cases we are going to discuss under pi form. Okay. Now, so in a pi form, so f of x is equal to the same series. There is no change in the series itself. But to calculate the Fourier coefficients, we have a slight deviations. Okay. So why that is a deviation, I will explain. Okay. So now, So in a pi form, as I told you already, there are two types of intervals of length we have to take. One is of 0 to 2 pi, another one is of minus pi to plus pi. So as I told you already, if you put c is equal to 0, definitely you get a naught is equal to 1 by pi integral 0 to 2 pi f of x dx, and a n is equal to 1 by pi integral 0 to 2 pi f of x cos nx dx, and bn is equal to 1 by pi integral 0 to 2 pi f of x sin nx dx. So if it is c is equal to 0, next if c is equal to pi, what happens? That is what we are going to see. Is equal to minus pi, then what happens? That is what we are going to see. If c is equal to minus pi means, as we see already, 1 by pi, internal limit changes from minus pi to pi f of x dx, and a n is equal to 1 by pi integral from minus pi to pi f of x cos nx dx, and bn is equal to 1 by pi integral from minus pi to pi f of x sin nx dx. So these two are the cases we are going to discuss. So in pi form, in 0 to 2 pi, so we don't have any more categories apart from this. So whenever the function is defined in the interval 0 to 2 pi, so we have to write the general expansion of Fourier series and calculate the values of a naught, a and b, and substitute in the series. We get the series, the problem will be over. Okay. Now in case of minus pi to pi, so we have either two categories, that is either it may be even function, odd function. That is in case of even function or odd function. So if it is neither even nor odd, if it is a even function and odd function, that is under half range series, that we are going to discuss under half range series. Okay. So if it is in minus pi to pi means we have three categories. If it is even, if it is odd, okay, take these two as different. If it is even, if it is odd, if it is neither even nor odd, then how can we calculate the values of a naught, a and bn? So look at here, in all these forms there is no change in the Fourier series. F of x is same. Okay, there is no change. But only the change is what is the formula to calculate the values of a naught, a n and bn. Okay, only the change in the Fourier coefficients alone. So what is the formula we can use to calculate the Fourier coefficients a naught, a n and bn? Okay. Now let me list out all the formulas under each of the interval that we have discussed in detail in this table. So f of x is the general Fourier series. This is the same for all. There is two types of intervals, 0 to 2 pi and minus pi to pi. So if it is in 0 to 2 pi, we make use of this a naught, a n and bn. So by making use of these three formula and calculate the values of the Fourier coefficients and substituting the expansion, we get the Fourier series. So if it is in minus pi to pi, so we have three categories. If it is even, odd and neither even nor odd. So if it is even, we calculate only a naught and a n, that's enough. No need to calculate the value of bn. So this I am going to explain when we are going to discuss the concepts under minus pi to pi, why this happened. Okay, I will explain in detail that. So if it is odd means you just calculate only bn value, no need to calculate a naught and a n, you directly take that is 0, because the property of symmetry this will happen. So I will explain this in detail when we are going to discuss the problems under the concept under minus pi to pi. Okay, if it is neither even nor odd means the same formula. Look at the 0 to 2 pi. So only the interval limits alone change from minus pi to pi. Okay, if it is neither even nor odd means we make use of these formulas to calculate the values of a naught, a n and bn. So with this short introduction, let me now complete about the introduction part of Fourier series, and I will see you in the next video in my examples under Fourier series under 0 to 2 pi. Thanks for watching. See you all again in my next video.